Hello, so today we are going to talk about space complexity. So space complexity is very analogous to time complexity, which we saw in a previous topic. It is basically, instead of classifying languages and problems according to the number of step time they take, here we classify languages according to the amount of space they take, which is basically the number of cells in a Turing machine, right? So you remember your Turing machine is composed of a series of cells, right? An infinite number of cells, but there is only a finite number of cells that are used for the input, like say 1, 0, 0, 1, 1, 1. So there is a sharp here, right? And then you have a bunch, an finite number of blank that follow. So if basically whatever you will have used on the tape, um, uh, whatever you've used to read and write or write, will be the space complexity, the space consumption of your Turing machine, right? So if you remember the examples we've seen so far of Turing machines that scan through the input and cross the 0, cross the 1, almost all of them, if not all of them, actually only used the space that is used by the initial inputs, nothing else, none of the blank afterwards. It could, some program actually need to use the blank, but the most basic one, the one we've seen, only use the n cells. So that means that the space complexity of this Turing machine is n, right? So that's the basic idea of space complexity. Now, it doesn't act at all like time complexity. It has a lot of interesting features that we're gonna look at. So it's really a very easy concept to grasp. It's just the amount of cells that have been used on the tape. And we also use asymptotic approximation, just like for time complexity. If we're not going to make the difference between n to the power of 3 or n to the power of 4, it's going to be just polynomial n to the power of k. And so we do this kind of approximation. 6n to the power of 3 is going to be n to the power of 3. Okay, so so the complexity is defined, or rather, the class of language corresponding to a certain space complexity is defined as space f of n for a deterministic Turing machine, and as n space f of n. Just like we had, before we had time and n time. So what does it mean? This means that this is the class of language. I mean, of course, it's going to depend on f, right? This is a type of class of language that use f of n cells with a deterministic Turing machine, and this is a class of language that use f of n cells with a non-deterministic Turing machine. So we'll see what's the difference between both. Of course, n space cannot be this class of language cannot be smaller than this class of language, because it includes at least the deterministic one, right? The non-deterministic will be at least as large. Another question is, is it going to be larger or equal? We'll see that later on. But first, to make this a bit more concrete, let's go through an example, the example of SAT. So SAT, remember, is a satisfiability problem where we have a Boolean formula phi. Say that this formula is x1 and x2 or x3, right? And the problem consists in finding, for any kind of input like that, an assignment of the variables such that phi or phi. I'm going to say phi, so it's more closer to the Greek. So that phi is true, right? So for instance here, if I do x1 true and x2 true and x3 false, it is an acceptable combination. Okay, so we know that SAT is NP complete, right? You remember from the previous chapter. So that means that SAT is definitely not linear and likely not polynomial, right? Um, so SAT is actually, in a sense, because of the way it's defined, exponential. By that I mean that, if you want really to find a solution, ultimately you're going to have to try all the values here, true or false, which is going to be 2 to the power of 3, right? Which is going to be 8 options for this specific formula. And of course, if you have 20 variables, it's going to explode, right? So it's in a sense exponential in the way it's designed. You can't really avoid a brute force search to find a solution. So now that's about time complexity, right? Now we're interested in space complexity. What is the space complexity of SAT? That means, if you find a Turing machine, what is the smallest amount of time that it will require the smallest amount of space it will require to be properly executed and find a solution, right? So try to think of a Turing machine that could solve the SAT problem, right? So imagine that we have, fees given as an input. So we're going to have x1 and parenthesis x2 or x3 parenthesis and then the blanks. How much are we going to use of this, right? How much space do we need, right? So imagine you scan through you head scan through, right? And maybe what your Turing machine can do is that every time you encounter a variable, you give it an assignment, right? Every time you encounter a new variable, right? If you encounter the same variable, you need to keep the same assignment. So for every new variable, and this is the input, we're going to say it's size n. So you give a value to each of these variables, right? You're not going to write over x1 because you need to keep x1 here, but you can write on the blank here. So say that you're going to start very methodically by assigning the value true to everything, right? And then you're going to change one true into false, and then you're going to change another true into false and another one, and then you're going to start over with one true into false and another true is switch into false, etc., until you have exhausted all 8 possibilities, right? That's going to be your exponential method. So you scan x1, it's a variable, and you go all the way to the end, and you're going to give it a value, right? You're going to say it's true, and then you scan. This is not a variable. This is not a variable, so you skip. This is a variable, and you give it a value, true, right? And this is a variable, true, right? And then you go back and you evaluate the whole thing for. I'm just making up, like off the top of my head, an algorithm for this. But again, we don't care about how much time it takes. We know it takes a long time, right? It's exponential. We care about how much space it's going to take. Well, in the end, eventually, I just need these 3 cells. That's all I need, because these 3 cells are going to store the current state of the assignments. And I'm going to go from true, true, true to false, true, true. I mean, until I find a valid state, right? And of course here true, true, true works, so it will be done. But if it doesn't work, worst case, I'm going to go through the 8 solutions, etc. Right? So, so what is my space complexity? It's n plus 3, right? It's n plus 3, so it's very small. It's so worst case, for any phi of size n, right? At worst, so basically the complexity here um, um, is going to be n plus m, right? We can say that SAT belongs to n plus m, right? It's in space n plus m. And we know that m is less, with m less or equal than n, right? It's not possible to have more variables than you have symbols in the initial inputs. So m is necessarily less or equal to n. So you can say that, you know, this is included. It's a subset of space 2n, right? So if we approximate, we can say that SAT is in space 2n, which is basically O of n, right? Because again, we use this approximation. We do not care about the details. What we're interested, to make it short, is it linear, polynomial, or exponential, right? So linear is going to be O of n. Polynomial is going to be O of n to the power of k, and exponential O of 2 to the power of n, right? So here, basically what we're saying, 2n is it's O of n, right? So we're saying that SAT is in space of O of n. So SAT is in linear space. So see the big difference, right? Linear is much more efficient than polynomial, right? This is much more efficient than polynomial. I mean, linear is part of polynomial, but it's much more efficient in general, than polynomial. So see the difference. We say SAT is, in terms of time, exponential. It's here, right? If you do linear, polynomial, exponential, SAT is here in terms of time, and it is here in terms of space. So there's a huge gap here. So because it's NP complete, right? It's basically, in a sense, exponential, and also because it's kind of the archetype, as we saw, NP complete problem. So how can we explain such a huge gap? And try to think about that. Why is there such a big gap between the time it's going to take? It's going to take a huge amount of time, right? You're going to have so many steps here, so many different configurations, but you only use so much amount of space, actually a very little amount of space. So how can we make sense of this big gap between exponential time and linear space, right? That's linear. Between linear space and exponential time. Well, a very simple reason for that is that space is reusable, right? I can switch here. Cell can take multiple values, right? So these 3 cells actually, even though it's only 3 cells, give me a great deal of power, of computing power in some sense, because I can reuse them as much as I want. I can switch, I can change. While time is not. Time is not reusable. So in some sense, you have here this very strong asymmetry between space and time with respect to computing that that the SAT problem reveals. And I'd like you to just think about that for a second, right? Space is reusable, time is not. That's a very basic thing of theoretical computing. It's also very philosophical if you think about it, right? This idea that any step in time is once it's used, it's, you could say, disposable. I don't like this expression because if it's wisely used, it's far from being disposable. It actually leads somewhere, but you cannot reuse it, right? So everything that has been consumed in time, it's consumed forever, while everything that is used in space can be reused, right? So think about that. That's something really powerful, and that's what is, in a sense, even though this sounds like a philosophical consideration, it is in a sense what makes the space complexity so different in its behavior, I would say, from time complexity. Okay. Um, so let's go back to the question of n-space, n-space versus space. So again, the definition of n-space is the class of languages or problem that can be computed in such amount of space, f of n, with a non-deterministic Turing machine. So first interesting question is, what is the relationship between these two? Is s-space equal to n-space, right? So that's the first interesting question, right? Do we have um, space of fn equals n space of f of n? So that's the first question. So in general, we know that it's not true because you can use you can use less space. You can save space using a non-deterministic Turing machine, right? Because again, just like for time, you don't accumulate the time from all the branch. You take just like for the time, you're going to take the largest time of the largest branch. Here you're going to take the largest amount of space of the largest branch that has been used for one of the branches. So with a non-deterministic, you can really, in some sense, demultiply the space you use. But the question is how much, right? So in general, we can say that we have this relationship, right? We know that we can at least do as much with a non-deterministic Turing machine that we can do with a deterministic. That's obvious. That's trivial to see. But again, what does this formula mean? This formula means that the class of languages that can be recognized in f of n amount of space is equal or smaller than the class of languages that can be recognized in f of n amount of space by a non-deterministic Turing machine, right? But the question is, what is the difference? And actually, the difference is not that big. This is given, actually, an interesting result in this respect is given by the Savitch theorem. That you can look in detail in the book if you want the proof. We won't see the proof here. It shows that any non-deterministic Turing machine using f of n amount of space can be converted into a Turing machine that uses only at most f of n square. So in other words, what this theorem says is that n space, right, the class of languages with a non-deterministic Turing machine that use this amount of space is included in space f of n square. So that means that if you can transform a non-deterministic Turing machine into a deterministic Turing machine, right? Again, when we don't put the d, when we don't put the n, that means d, that means deterministic. The amount of space, you can translate it into a deterministic Turing machine using only the square amount of space, right? So if you use n here, you're going to use n squared here at most. So let's make sure we understand that what this formula means, right? That means that again, when I use a non-deterministic Turing machine for any language that can be recognized using this amount of space with a non-deterministic Turing machine, you can also recognizing using this amount of space, using a deterministic Turing machine. Okay. So we already said that space is necessarily smaller than n space, smaller or equal. And now we say that n space is smaller or equal than space of the square amount of space. So if we combine those, we have space of f of n. So basically what I'm saying here is that n space is somehow in between space and space of the square. So if you want to compare n space to its deterministic Turing machine equivalent, it's going to be somewhere between the same thing with a deterministic Turing machine and the deterministic Turing machine using not twice as much space, but square as much space, right? The amount of space to the square. Okay, so we're gonna try to unfold this because f of n is a bit abstract. We're gonna try to unfold this by trying to consider f being in one of these cases, right? So far we've made the assumption on f being, we've not made any assumption on f, right? Being either linear, not exponential, polynomial, sorry, or exponential. And we're gonna now make this assumption to see how the theorem, what it tells us about the relationship between space and n space, given one of these three cases. Okay, so let's look at the impact of the order of magnitude of f. Let's first take the case f linear, right? We're going to start with the case where f is linear. So if f is linear, well, we're talking about space. Now we're talking then about space O of n. And I don't know if you remember, but space O of n is exactly the class of languages recognized by an LBA. LBA recognizes these languages because LBA is, what does LBA means again? Linearly bounded automaton, right? Linearly. So this is what it means. You bound the Turing machine linearly. You give it a linear limit. So so space of O of n is nothing else than the class of languages that are recognized by a linear bounded automaton, right? Which is nothing else than linearly bounded Turing machine. So remember that on the topic of LBA, the topic 6, we hit our first big question, the big interrogation of computing theory that is still yet to be solved. P equal NP being our second big question, right? And the first big question was, we don't know if LBA and non-deterministic LBA recognize the same language, right? Right? So you remember, for instance, we know that for finite automaton, they recognize the same language. We know that for PDA, they don't. We know that for Turing machine, they do. But for LBA, we don't know. We don't know. We have this question, we don't know. Well, this question can also be written in our new terminology here as, do we have the following equality? Space of O of n equal n space of O of n. And I'm putting, question mark here to make sure that we don't know the answer, right? It's yet to be proven. So how does this mean the same thing as does LBA and NLBA recognize the same language, a class of languages? Well, these are classes of languages. This is a class of languages that use linear space, that have linear space complexity. This is a class of languages that have linear space complexity with a non-deterministic Turing machine. So this is the same question basically, right? Um, so now let's look at Savitch theorem for F linear. What does it tell us? If we put this into our linear context, we have space O of n. Well, that's Savitch theorem is properly the last part of this, but I repeat that even though it's obvious. N space O of n, and I say this is obvious. It's this means really if it's not equal, this will have to be smaller by definition, because again, non-deterministic is at least cannot be less powerful than the deterministic, right? Remember that. And this is included in, that's the Savitch theorem, properly speaking, O of n square, right? It's O of n square, which is equal to O of n square, right? Now, when I say that, that can confirm that we really can't tell if a linear n space contains more languages is larger than this or not, right? Because in one scenario we see that if you take this closer to this border, it is equal, right? For really n space to be larger than this, n space linear, right? To be larger than space linear, you would have to jump to this kind of thing, to at least n squared, which is really, n squared is really kind of the beginning of polynomial, right? It's the smallest polynomial you can have is O of n squared, right? So in some sense, the very limit, the maximum that n space can be, n space linear can be, is really the minimum. In some sense, it would need to not be equal to that. So it's really stuck in some sense something very small, very tight margin. And this is why we can tend to say that this is probably equal. But again, we don't know. We just know it's a very tight space. So I just wanted to relate now the Savitch theorem, what kind of insight it gives us toward this LB equation we've seen before. Okay, so that's for linear. So for linear, basically, we don't know, but we know it's close, right? We know it's close. Now, for polynomial, what can we say about, if we have a f polynomial, what can we say about the relationship? Well, if we have polynomial, we then have space. So here it's important because we're gonna give some definition. We have so space of O of nk, right? So that's polynomial space, and this is equal by definition to what we call PSPACE. So it's the space equivalent of the P in time complexity, right? And n space of O of nk is called NPSPACE. And so this is, of course, the space equivalent of NP in time, right? So instead of saying P time, we just say P. Instead of saying NP time, we just say NP. But for space, we put the complete denomination, PSPACE, NPSPACE, to make sure there's no confusion. Okay, so basically space is polynomial space, NPSPACE is polynomial space with a non-deterministic Turing machine, right? Remember, n doesn't mean non-polynomial, np doesn't mean non-polynomial, right? It means polynomial space with a non-deterministic Turing machine. Okay, so I hope this kind of loop back nicely to what we've seen in time complexity before and makes sense. If it doesn't, please let me know and don't hesitate to ask me questions. Now, how can these two compare? Still an interesting question, right? We have several solutions, right? Either we can say that, and take a minute just to try to think about it and try to make sense of it. So either it's included, NPSPACE, sorry, or we have PSPACE NPSPACE equal NPSPACE, so either included or equal, or again, it cannot be the other way around because n is always at least as powerful as deterministic again, or we don't know, right? Like it's the case for time, by the way, polynomial time, or like it's the case for linear space. We don't know either, right? So that's an interesting question, and I invite you to just take a minute to try to think about it and say what you would say about that. Not a full minute though. Well, let's look at Savitch theorem for f polynomial, and it should give us a clue. So now if I copy this theorem for polynomial, I have space of polynomial space is included in polynomial n space, which is included in space. Sorry, it's really small. I'm gonna write it here. Included in space of polynomial square again, which is going to be nk square, which is n to the power of k, n to the power of 2k, right? Okay. Now, if I use my new terminology, by definition, right, this is PSPACE, so I'm going to rewrite this. We have PSPACE is in NPSPACE, and it's in, and so what is this? Space of O n to the power of 2k. Well, it's polynomial space, right? There's no difference between n to the power of 2k and n to the power of k with respect to our asymptotic approximation, right? This is both polynomial, this is polynomial, this is polynomial, right? Just because this actually is a kind of a polynomial operation, it's polynomial times polynomial is polynomial. So this is PSPACE. So this is PSPACE. So what I'm saying is that NPSPACE is basically between PSPACE and PSPACE. So this is NPSPACE equal PSPACE, right? That's the obvious result of that. So PSPACE equals NPSPACE. So that's a very interesting result because this differs from what we had with the linear time, or what we had with the polynomial, with the linear space, or what we have with the polynomial time, right? It differs. In both, we didn't know. Here we know. Again, I'm trying to explain the reasoning here. We know that NPSPACE is at least as big as PSPACE, right? But because of Savitch theorem, we see that NPSPACE is at the biggest PSPACE, because space of O of n to the power of k to the power of 2 is n to the power of 2k, which is also polynomial. So if it's polynomial, this belongs to PSPACE. So NPSPACE is greater and smaller than PSPACE. I mean, it's greater or equal and smaller or equal than PSPACE, which means it can only be equal to PSPACE. So what we're saying is that with respect to polynomial space, using a Turing machine that is non-deterministic or deterministic doesn't change anything. It's exactly the same. It's exactly the same space that is used, right? So that's a very interesting result. Now we can do the same thing for exponential, and then we can look at the relation between P and P and PSPACE and PSPACE, between time and space, and we'll do that in the next video. Thank you very much.